Hello, welcome to the sixth and final lecture in my series on the coronavirus. In the first 5 lectures, I covered topics including how coronavirus gets into cells, how the coronavirus copies itself inside of cells, and how our immune system responds to a coronavirus infection. Now, I'm going to try to pull all of that information together that I explained to you in the first set of lectures and describe how we can use that information to potentially develop treatments, develop therapies to blunt the progression of a viral infection. In lecture 5, I focused on therapies that involve engaging the immune system, either passive immunization or vaccination. In this lecture, I'm going to describe the other various approaches that one can take to blunting the progression of viral infection. And so we've already covered the immune system in lecture 5. Here I'm going to cover antivirals, so drugs that would target components of the virus itself to block its replication, and also anti-host factors. So the virus also has to make use of proteins in the host in order to duplicate itself, and so those also potentially become targets. So if you remember from an early lecture, for the coronavirus to get into cells, it has to dock onto ACE2, and then it either enters directly through the plasma membrane or it gets incorporated into an endosome and then enters the cytoplasm from the endosome. And so out here in the plasma membrane, one can envision that there's at least 2 host factors that one could potentially target, and that would be ACE2, the receptor for coronavirus, or the protease associated with the membrane of cells in the lung that cleaves the tether on the coronavirus spike protein to enable it to reorient in a configuration that will enable it to penetrate the membrane and fuse the coronavirus with the cell membrane. So these are both potential targets. However, whenever thinking about host cell targets, it's important to remember that those targets weren't put there just for the coronavirus to exploit. They have a function that they carry out in the human body, and if you direct drugs against these proteins and you block that function, that could end up even exacerbating the disease instead of helping. And so one has to be very careful in thinking about these kind of targets, although they are potential targets to bear in mind. Now, if the coronavirus enters into the cell via an endosome, there's yet 2 more host targets that one could aim for. And this would include, so let me put a purple X on targets that we've gone after. So ACE2 and this extracellular protease I already mentioned. Inside the cell, I mentioned how the endosome gets acidified, so it becomes more like vinegar, it becomes acid. And that's important to activate a protease in the endosome that will cleave the spike protein to activate its ability to fuse the virus with the membrane. And one could block that acidification step, and I mentioned chloroquine and hydroxychloroquine do that. Or one could also potentially block this protease here that works inside the endosome. Again, there's the risk here of targeting host cell factors, and there's also the issue that there's 2 potentially different ways coronavirus can get inside of cells. So if you block the pathway out here or the pathway in here, you still have the other pathway that's operating. And we don't know yet whether you would absolutely need both pathways in order for productive infection to continue. Now, once the coronavirus genome enters into the cell, so this is the positive strand RNA, the first thing that happens is you translate this very long polyprotein that has, for the bigger version that's made, at least 16 proteins linked together. And then if you recall, the first thing that happened is it gets snipped to release the 16 individual proteins, and that's carried out by these molecular scissors, these proteases that are part of the polyprotein. And we know from other viruses, for example HIV, that the protease of HIV is essential, and many of the HIV drugs, cocktails, involve inhibiting that protease. So you could imagine making inhibitors that target one or both of these proteases that would block the processing of this polyprotein, and that could be another strategy for blocking replication of the virus. Now, targeting viral proteins is in a way more attractive because if you can make an inhibitor that's really, truly specific, it should be better tolerated than inhibiting one of the host proteins, because in theory you could inhibit just that one viral protein and no other proteins, and then you would have an inhibitor that should be well tolerated by the host. Now, the other thing that happens to the RNA after you make this polyprotein is it gets copied to make a negative strand. So now you have a long double-stranded genome. And then after that gets copied, the negative strand is used as a template to make a series of positive strands, and these will be part of viruses that are assembled later on. Now, in addition, you make these short negative strands that are copied again to make short positive strands, and these are then RNAs that express the major structural proteins of the virus, the S, E, M, and N protein. And these events here, the making of the negative strand, and then the copying of the negative strand to make positive strands, and then the production of short negative strands, and from them short positive strands for producing these proteins. All of those steps are carried out by an enzyme of the virus known as the RNA-dependent RNA polymerase. And that's a key enzyme in copying the virus. We know in other viruses, including HIV, for example, that you can target that enzyme with drugs, and if you block that enzyme, again, you can block the replication of the virus. And so that enzyme represents another very attractive target that would enable you to knock out all of these various steps in the viral life cycle. So these are probably some of the most attractive targets, although bear in mind that the viral genome encodes 29 different proteins, and viruses tend not to encode proteins that they don't need to use. And so in principle, many of those 29 proteins could potentially serve as targets to block the progression of viral infection. Now, one final approach that I'll describe is to blunt cytokine storm. So what was mentioned in a prior lecture is that sometimes the immune system mounts a response to an infection that's overexuberant. And so a large number of different cytokines are produced. Those cytokines can act on immune cells, innate immune cells, and normal tissue cells, and cause a number of major changes that could lead to profound inflammation. And that inflammation can have a number of negative consequences. Normally, it has a positive effect, but if it runs out of control, it can begin to have a negative effect that only exacerbates the infection by the virus. And so sometimes tamping down that response can lead to benefit. And so that's another strategy that's being explored. There's a number of drugs that target either cytokines or the receptors that cytokines bind to that could potentially blunt cytokine storm in a patient with coronavirus, which could, in some circumstances, potentially yield a benefit. Now, one thing to bear in mind is there's going to be a lot of ideas, a lot of proposals, and many of those ideas may be good ideas, but nature has a way of humbling the overconfident. And it's important that these ideas be tested in rigorous clinical trials, because you can't fool nature. Nature will do what it will do, and it will be important to document that whatever drug is developed has the activity we think it has by proving that in clinical trials. Now, I'd like to say goodbye. It's my final lecture. I hope you enjoyed these lectures. It's been a pleasure for me, and I hope you learned something, and take care. Have a good day. Have a good month. Have a good year. Bye.